Bismillahirrahmanirrahim. Assalamualaikum everyone. Today we are at lecture number 19 for week 10. These are the topics for today's lecture. This is section 10.6, 10.7 and 10.8. These are the sections that we will go through one by one. What we are going to see in this lecture that we are going to study the open specifications of a practical open. What are the important parameters of a practical open? We have started the open, considering the open as an ideal. And see that the ideal gain of the open is infinite, input impedance is infinite, and output impedance is 0. And some other important parameters that we are till now idealizing those parameters, and we didn't see any impact of those practical imperfection in an open. And only the idealized characteristics of the open are considered. But from now onward, we are now taking the real practical open and its parameter into account, and see what these parameters would affect on the output of the open, as well as on the limitation of the use of the open in different applications. What are these limitations, and what are the depending upon the requirement of the application, which open is more suitable than the other, that is decided on these parameters. And these parameters are important for a particular application, which meet the requirement of the application and meet the required specification of the open. So these are the few categories based on these parameters. DC specifications are divided. One are the DC offset parameters. One are the frequency parameters. DC offset parameters are related to the DC voltages and currents, and the frequency parameters are related to the bandwidth of the amplifier, what is the lower cutoff frequency or higher cutoff frequency of the amplifier, and the bandwidth of the amplifier. And another important parameter, frequency parameter, is the slew rate of the operational amplifier, that we will see in this class what is the slew rate. And lastly, we will see the open unit specifications of a particular open, in which a special case of 741 open will be considered. That the specification sheet of a 7.4 open is given, and what are the important parameters of a 741 open which are specified on its specification sheet, like its DC offset parameters, frequency parameters, common mode rejection ratio, input impedance, output impedance, supply voltage limitations, power limitations, input voltage range, what is its maximum, what the open output maximum current it can provide for a particular load. These are the important parameters that are specified on its data sheet. So for every open, there is an associated data sheet that is provided by the manufacturer, and you have to select a particular open by looking at its specification sheet, and and choose your required op-amp for your application which meets the desired characteristics or desired parameters of a particular op-amp in your application. So we are at chapter 10. A few topics we were not covered in chapter 10. We are getting back to those topics now and see that are covered in these sections. So go through these sections and see these important characteristics of the op-amp. So what are the DC parameters? These are the DC offset parameters, offset voltage, offset current, bias currents. So and the impact of the offset voltage on the output of the op-amp. These are the frequency parameters, gain, bandwidth, and slew rate, and then at the end we will see the data sheet of the op-amp. So ideal versus practical op-amp. So ideally the output from an op-amp should be 0 when we apply 0 volts at the input of the op-amp. So for op-amp in which its inputs are at 0 potential, that is both input terminals are grounded, then there would be no input voltage applied, that is Vt would be equal to 0. So whatever the gain of the op-amp, the output should be 0 as well because of the fact that input is 0. So ideally the op-amp should produce an output which should be 0 for the input of the op-amp being at 0 volts. But practical op-amp, due to the input offset voltage and input offset currents, the output of the op-amp is not 0 even when both inputs are ground. So even the input of the op-amps are at ground, 0 potential, even that the practical op-amp will produce some output. That output would not be 0. Ideally it would be 0, but practically it would not be 0 due to these offset parameters of the op-amp that are not 0 for as per the ideal case. So practically the offset voltages and offset currents causes an error voltage at the output, which should be 0 for the ideal case. Similarly, for an op-amp connected in the feedback, negative feedback, and if you apply 0 input at either terminal, whether it is inverting amplifier or a non-inverting amplifier, with input equal to 0, it should produce an output equal to 0. Whatever the gain of this inverting or non-inverting amplifier is, output should be 0 for input to be 0. But in a practical op-amp, due to its non-ideal characteristics of the offsets which are built in within the op-amp, the output of the op-amp would be non-zero, and there would be some finite output even with input 0. So we want to see what are these offset voltage and currents, and what is the impact on the output due to these offset parameters. सो जो ओपन है उसकी जो आइडियली जो आउटपुट है वो ज़ीरो होनी चाहिए अगर इनपुट ज़ीरो है, बट जो प्रैक्टिकल ओपन है चूँकि उसके अंदर बिल्ट इन एक एरर वोल्टेज अपीयर होती है उसकी इनपुट के ऊपर, या फिर जो इनपुट करंट है ऑफसेट करंट जो कि अपीयर होता है इनपुट टर्मिनल्स के ऊपर। लेटर हम देखेंगे कि ये ऑफसेट करंट किस वजह से यहाँ पे बिल्डअप होता है इनपुट टर्मिनल्स के ऊपर। तो इस एरर वोल्टेज की वजह से जो कि इनपुट टर्मिनल्स के ऊपर अपीयर होती है, और जो करंट है एरर करंट जो कि इन दो टर्मिनल्स के दरमियान पे अपीयर होता है, इसकी वजह से जो आपकी आउटपुट है वो जो है वो ज़ीरो नहीं होती, एक एरर वोल्टेज यहाँ पे प्रोड्यूस होती है। और आप चाहते हैं कि जो ये एरर है इसको आप किसी तरह से मिनिमाइज कर लें और इसको ज़ीरो कर लें। सो क्योंकि अगर इनपुट ज़ीरो है तो आउटपुट भी ज़ीरो होनी चाहिए। अगर कोई पहले से यहाँ पे आउटपुट आ रही है तो वो एरर कंसिडर होगी और इस एरर को आप ख़त्म करना चाहेंगे या मिनिमाइज करना चाहेंगे, तो सो दैट देयर शुड नॉट बी एनी आउटपुट फॉर ज़ीरो इनपुट। सो चाहे वो ओपन नेगेटिव फीडबैक में है या ओपन लूप में है, तो इन एनी केस your requirement is that output should be zero or input to be zero, because these circuits are used to measure the output quantity in different applications, and if output is in error then there will be a problem for measure the quantity. The quantity which you are measuring would be in an error due to these offset voltages. So it is important to figure out this phenomena of op-amp behavior, that op-amp will produce an error voltage. Practical op-amp has an internal problem because of which it will produce an error voltage at the output even there is no input. So the op-amp manufacturer specifies the values of input offset voltage and current on its data sheet, and it also provide you the mechanism by which you can reduce the offset error that we will see later. So, for example, for a 741 op-amp, the data sheet of this op-amp specifies the input offset voltage. It has typically the value of 1 millivolt, and it can be a maximum of 6 millivolt. So, input error voltage that is produced at the input terminals of this much magnitude. And if the op-amp has a very large gain, then you can think of the output error voltage that can be here for this much input. Specifically in the open loop gain, you know that even input error voltage of a microvolt can bring the op-amp into saturation, and a very large output can be here for a very small input. So input offset voltage is have a very significant effect on the output. So it is important to see the value of the op-amp's output, whether it is due to the input offset error voltage or because of the desired input. So it is to ensure that there should not be any output voltage due to the zero input at the op-amp. That is, when you are not applying any input, output should be zero. Similarly, for the another parameter that is known as input offset current, and it is defined as it is denoted by IIO, that is current, which is input offset, and it has a typical value of 20 nanoamperes, and it can be maximum of 200 nanoamperes. Similarly, we will see later on what is input bias current, common mode rejection, common mode input voltage range, and the maximum of the output voltage swing, open loop differential gain, input resistance, output resistance, capacitance, common mode rejection ratio, and what is this maximum supply current that it can provide, and what is the total power dissipation the current can handle. So it is in milliwatts. And some other parameters, frequency parameters, that are also specified in data sheet that we will see on a detailed data sheet of 741. We are now looking into the output offset voltage due to the input offset voltage and input offset current. So the output offset voltage is produced due to any of the parameters. So first of all, we will be trying to see the effect of input offset voltage on output of the output. So output offset voltage due to the input offset voltage that we are going to consider. So to determine the effect of input offset voltage on the output, we are going to consider the following circuit, in which you can see that the both inputs of the open configuration is grounded, that is no input is applied either on inverting side or non-inverting side, but an internal offset voltage that is appeared at between these two terminals of the open input is defined here with this voltage source, and that is the input offset. This input voltage source is not applied externally, but it is the part of the IC. This is internal to the IC that appears at the input terminals, and because of this input offset voltage, we are modeling it as an input battery or input DC source. This is a DC source of value 1 millivolt to 6 millivolt for a 741 open. And if this much voltage is appeared at the input, then what would be the output? That would we are taking it at the non-inverting terminal. So considering this open as a non-inverting amplifier, the gain of the non-inverting amplifier is 1 plus RF over R1 into input, and input is the VIO. So based on the values of these resistances, we will be getting the output due to this input offset voltage, and that output voltage will appear at the output of the open as an error. So in a both circuit, the open is connected in negative feedback with both inputs are grounded, and input offset voltage, which is internal to the open, appears as an input voltage source, and we can determine the output from the beginning circuit as follows. That will be out equal to A into VI, where A is the differential gain of the open and VI is the differential input. V plus minus V minus. So Vi is the voltage at this terminal minus voltage at this terminal. So voltage at this terminal is VIO, and voltage at this terminal would be equal to the voltage divider voltage across R1 that can be computed using voltage divider formula. That is V0 into R1 divided by R1 plus R. So this is the R2 voltage, and if we solve it for V0, we will get this expression. And from this expression, if this AV is very large, then this large value is multiplied by this factor, and still this term will be very large as compared to 1, and this one can be ignored, and this A is cancelled with this A, and the resulting circuit will be the output offset voltage is input offset voltage into R1 plus R2 divided by R1, which is 1 plus R1 by R1. That we have already know that if this is an unlimited amplifier, then the gain of the numerator amplifier is 1 plus RF over R1, and output will be equal to gain into input. So this equation shows how the output offset voltage results from the specified input offset voltage for a typical amplifier connection of let me see an example that calculate the output offset voltage of this circuit. The open specification needs an input offset voltage of 1.2 millivolts. So from this given data, we can use this relationship of the output offset voltage that input offset voltage into R1 plus RF over R1. Input offset voltage is 1.2 millivolts. R1 is 2 kilo ohm, RF is 150 kilo ohm, and if we plug these values, we will get an output of 91.2 millivolts at the output. Even the input applied in this case is 0. That is, this input is not applied in the circuit. Only the input offset voltage is considered, and that because of this input offset voltage, we will be getting an output arrow voltage of 91.2 millivolts. Next is what is the output offset voltage due to the input offset current. So because of the input offset current, the open output would be non-zero. There would be a certain offset voltage even the inputs of the circuit are grounded. That is, no input is applied, even then will not be equal to 0. So why this output is not equal to 0? This is because of the input offset currents that flow into the input terminal of the op-amp. So ideally these currents should be 0 at both input terminals of the op-amp, but practical op-amp has a certain finite non-zero current that will flow into the op-amp terminals. So even this current, magnitude of this current is very low. Still, because of the fact that the input impedance or input resistance of the op-amp is not ideally infinite. So whatever the current flows through this input resistance, there will be a small input voltage that appears across this resistance, and it turns out to be appearing at the input terminals of the op-amp, and with this very small input voltage that appears and a large gain of the amplifier, you will be getting some non-zero output at the op-amp. So these currents which are practically non-zero because of the fact that these are the so if you remember that the input stage of an op-amp is a differential stage, और जो differential stage के अंदर जो input जहाँ पे सिग्नल अप्लाई करते हैं वहाँ पे एक डिफरेंशियल पेयर आप ट्रांजिस्टर का एक डिफरेंशियल पेयर यूज़ होता है और इनपुट आप ट्रांजिस्टर की बेसिस के ऊपर अप्लाई करते हैं। जब भी आप ट्रांजिस्टर की बेसिस के ऊपर सिग्नल अप्लाई करेंगे तो जो बेस करंट फ्लो करेगा उसकी वजह से इलेक्ट्रिक करंट फ्लो करेगा और मीटर करंट फ्लो करेगा, ट्रांजिस्टर को फ्लो करेगा। That base current is the input base current of each differential amplifier that would flow into the input terminal of the op-amp. So this input current of our differential input stage is always non-zero, and these two input currents are slightly different because of the fact that the transistors you are using in a differential pair are not identical. And so a slight difference in the transistors, in their beta value, in their characteristic, these two currents will be slightly at some difference. So this current and this current are not equal. So if they are not equal, then there will be a net current that would be established through this input resistance. Ideally, these two currents should be equal. That is, the two transistors of the input stage of a differential amplifier should be perfectly matched and should have same beta value and same characteristics, so that these two currents are equal. And if these two currents are equal, then the net current through this resistance will be zero. Whatever the current is coming from top to bottom, it will be equal to the current that is flowing from bottom to top. And if these two currents are equal, then net current through this resistance will be zero. But if there is a slight difference in these two currents, then the difference between these two currents would be non-zero. And if the net current in any direction through this resistance flows, then the voltage across this resistance will be that value of the current into the resistance, and that voltage appears between these two input terminals due to the input bias currents. So these are the input bias currents that are established at the input terminals of the op-amp. And because of these input bias currents and the voltage produced due to this input bias current, the output of the op-amp will be some value other than zero. So an output offset voltage will also result due to any difference in DC bias currents at both inputs are built in. Since the two input transistors are never exactly matched, each will operate at a slightly different current. The input bias currents are indicated in this figure. So with input bias currents as indicated in the previous slide, we can represent the associated voltage across each input resistors as shown in figure. So if there are some input bias currents in this terminal or in this terminal, then you can see that if there is some current flowing in this terminal, then there will be some voltage across this resistance. Similarly, if there is some current flowing in this terminal, then this current flow would eventually is coming from this resistance or from this path. And if we consider this resistance to be very large as compared to this, then this current will be immediately small, and it would be assumed to be zero. So majority of this current is contributed from this coming from this path, and the voltage across this resistance will be with this polarity, and it will be equal to I bias negative into R1. This voltage drop will be equal to I input bias positive into RC. So a positive bias into RC, the voltage across this, and this voltage across this will be in this case. So with input bias currents as indicated in the previous slide, we can represent the associated voltage drop across each resistor as shown in figure. These are the voltage drops across each resistor, and with these inputs indicated, we can determine the corresponding output using superposition. So if we have these two input voltages, we can find the corresponding output due to these two inputs using the superposition theorem. That is, we consider each input one by one and correspondingly find the output for each input, and then at the end add the result due to adding. So first of all, if we consider this voltage and turn this equal to 0, then this becomes a non-inverting amplifier with input applied at the non-inverting terminal, and this terminal is grounded. So the output will be equal to input times the gain is 1 plus R over R over 1, and input is IB plus into RC. Similarly, output due to the input bias current on the negative side will be equal to make this voltage equal to 0 and keep this source intact. The output due to this input will be equal to 2000 of output input required at the inverter terminal, and non-inverter terminal is grounded. That will be counted inverting amplifier, and the pair of inverting amplifier is minus R over R1, and the output will be equal to A into input and negative into R. So this is output due to the non-inverting input, and this is output due to the inverting input. The total output also voltage will be equal to the sum of these two, and if we add these two inputs, adding these two outputs, load plus and load minus, we end up with this relationship. In this relationship, we can see that since the main consideration is the difference between the input bias currents rather than the magnitude of the each quantity. So whatever the value of each bias current is, as long as they are equal, then there would not be any offset current at the input, and there would not be any offset voltage. But when there is a slight difference between these two currents, then input offset current is established, and that causes the output offset voltage. So main consideration would be for their difference. What is the difference of these two input bias currents? That is important for us to have an impact on its value on output offset voltage. So we define a difference of these two currents as input offset current, and that is equal to I in positive minus I in bias negative. Usually the magnitude of this difference is considered. Whatever the bias current is greater, the difference is considered as a magnitude. So again, secondly, since the compensating resistor RC is usually approximately equal to R1, that is these two resistors are chosen to be approximately equal. This resistance is introduced to reduce the impact of input bias current. So this resistance is added for that purpose. So the selection of this resistor is such that this is approximately equal to R1. So whatever the value of R1 is, you choose corresponding value of RC. So if these two are set equal, then you can simplify this equation. If this is RC is equal to R1, this becomes R1, then this will be cancelled with this. This is also cancelled with this. Then this output offset voltage will be equal to I in positive into R1 plus RF. First we take the LCM, and then you can cancel it, and this value will become R1 plus RF, and minus I in negative into R, which can further be simplified as considered another assumption that the value of RF is chosen to be very higher than R1, so this can be ignored, and this equation becomes equal to I in positive into RF minus I in negative into RF. So take RF common, then it will be RF into I in positive minus I in negative. So output offset voltage equation is reduced to this simple form, that is equal to RF into I in offset, which is difference in these two currents. So this is the equation that can be used to find out the effect of input offset current on the output of the op-amp. It will be equal to RF into input offset. So now calculate the output offset voltage of the circuit shown in figure 1043 for op-amp specification. Listing the input offset current to be 100 nanoamperes. So if input offset current is 100 nanoampere and circuit is given to be in figure 10.43, Now that we take an example for input offset current, calculate the output offset voltage for the circuit shown to the time for 5.43 for open specification listing input offset current of 100 nanoampere. So for this open, the input offset current is that established between these two input terminals. So this input resistance is 100 nanoampere, and if the circuit is connected in negative feedback with this input equal to 0, then what will be the output due to the input offset current that you can compute using the equation derived in the last slide, that output offset voltage is equal to input offset current into the feedback resistance RF. So this is given as 100 nanoampere, feedback resistance is 50 kilo ohm, then the value turned out to be 15 millivolts at the output. Now what would be the total offset voltage due to the input offset voltage and input offset current that we can compute using this relationship, that total offset voltage will be equal to offset voltage due to the input offset voltage and the output offset voltage due to the input offset current. So the total offset voltage of the open is due to the input offset voltage and input offset current of the open. And you can use this relationship to find out the total offset voltage due to these two input DC parameters. So let's take an example that calculates the total offset voltage for the circuit shown in figure for an open with specified values of input offset voltage is 4 millivolt and input offset current is of 150 nanoamperes. So we can with this input equal to 0, what will be the output due to these input parameters? So we can compute the output offset voltage due to input offset voltage using this relationship. This will turn out to be 404 millivolts, and then compute the output offset voltage due to the input offset current, and it will turn out to be equal to input offset current into RF. RF is 500 kilo and input offset current is 150 nanoamperes. So plugging these values, we will get 75 millivolts due to the input offset current. This is due to the input offset voltage. So total output offset will be equal to the sum of these two input offset and sum of these two output offset voltages. That will be equal to 471 millivolts at the output of the open, even when you are not applying any input to the circuit, but because of the internal parameters, non-ideal effects, the open output of the open will be in an error of this much. This much voltage will appear at the output of the open due to the internal effects. Another parameter which relates the input bias currents of each terminal of the op-amp is called the input bias current, and it is defined as the average of these two input currents, IB positive and IB negative. And this input bias current is specified on the data sheet of the op-amp. One could determine the separate input bias currents using the specified values of input offset current and input bias current, which we can relate these two parameters to determine the current of each terminal of the op-amp. So this relationship is obtained by considering this condition that IB positive is greater than IB negative. So if IB is positive, the current at the positive terminal is greater than the current at the negative terminal, then this relationship can be derived using this relationship I input bias, and the second relationship that is for input offset current, and that is input offset current is equal to IB positive minus IB negative. So you can derive this relationship, and if we have this equation, we can find the individual terminal currents of the op amp if you know these currents, and these currents are usually specified on the data sheet. So next we see an example to apply these equations to find out these individual currents. So calculate the input bias currents at each input of an op amp having the specified values of input offset current and input bias currents. So just by plugging these values, you can find out the individual terminal currents of the op amp to be this much. These frequency parameters, next topic is that we would cover in the next class, inshallah. That's it for